Alright, today, circle mensuration. Mensuration is just measurement. Alright, so circle measurements is what this is about. So some definitions of some things. So here's some circles. I marked all the circles, the centres with this O. And so if you draw a line across from one side of the circle to another, excuse me, that's called a chord. So it just joins any 2 points on there. And that chord, it divides the circle up into 2 parts. They're called segments. You've got a small one or a big one, minor and major. Okay, so if you draw some radiuses, so from the center to the outside, there's some radiuses. Then you get this wedge cut out of the circle. And so these wedge shapes are called sectors. And again, the small one's the minor, the big one's the major. All right, let's see what we got now. Arc length. Okay, so the arc length, as we got here, this is the distance around there, the arc length, so A to B. All right, and it's part of the circumference of a circle. So it's part of a circle. So if you've got the circumference of circle is 2 pi r. So if you've got a certain number of degrees in the middle, and of course the whole circle is 360, so that fraction of a whole circle is that fraction of the whole circumference. Now if it's in radian, it's a little bit simpler than that, because it's just your radius times by whatever the angle measure is in radian. All right, so there, arc length. Chord length, so that's this length here, A to B, and this is the formula for that. 2 lots of r sine theta on 2, and that comes from, if we put a line across here and make a right angle triangle, then this angle's theta on 2. This side is the sine, so r sine theta on 2, and then of course this down here is the same. So you've got 2 lots of them. So that's where that all comes from. All right, so chord lengths, areas of a sector. So again, the same thing for the area of a whole circle. We know is pi r. Well, pi, shouldn't have put that there. Is the whole circle is pi r squared, of course. And so if we've got a fraction of a circle, so theta over 360, theta degrees out of 360, so then that's that. They just write it differently to that for some reason. So that's if your angle's in degrees. If your angle's in radian, then it's a half r squared theta, where theta is measured in radian. All right, so let's have a look at using some of these things. So first of all, the exact length of chord AB. I'm going to change my thing here. So chord AB is, let me see if I can draw a line. So AB is from there to there. So that's my chord AB that I'm looking at. All right. And so I want to know the length of that. So the length of the chord, chord length is 2r sine theta over 2. So the radius there is 10. So it's 2 times 10 times sine of 120 over 2, which of course is 60. So that's just 20 sine 60. And when you do that, you should always, it says exact length anyway, so okay, so that's 20 sine of 60 root 3 over 2. 2 goes into there, once there 10 times, so 10 root 3 centimetres is our chord length. Okay, next, exact length of the arc, so that's this distance around here. Alright, so I'll do them there. And so the formula for that, it's in degrees, so it's theta over 360 times 2 pi r. So theta is 120 over 60 times 2 times pi times the radius is 10. 360, not 6. Oops, I've done that wrong too. It's 360. Alright, so 12 goes into there 10 times. Goes 30 times into that. What else have we got? We can also cancel. Well, no, actually, yeah, because 10 goes into itself once and into there 3 times. So we've got 1/3 times 2 times pi times 10. So on the numerator, I've got 2 times pi times 10, so I've got 20 pi on the numerator. And the denominator, I've got 3, and that's centimetres. And it asks again, I believe, for exact. Yep, so we leave the pi in, we don't put the decimal approximation. All right, so last bit is the exact area of a sector. And so it is pi over 360 r squared theta. So pi over 360 times 10 squared times theta, which is 120. And I should have got that right before, because 120 goes into itself once and into there 3 times. So we'll have 100 when we square the 10 pi over 3 centimetres squared for our area. All right, so it's just a matter of plug and play numbers. All right, there is the area of the segments. So I haven't. So we've said area of sector. We've got chord length here. We've got arc length, but I haven't looked at these segments, the areas of the segments. So area of a segment is the next bit here. And so again, there's 2 versions depending on whether we have our angle in degrees or in radian. But effectively, what we do is we work out the area of the sector, just this bit, and from that we take away the area of this triangle. And remember, the area of the triangle, 2 sides and the angle between, half of the product of the 2 sides and the sine of the angle in between. So that's what this bit is on the end. All right, so in degrees, to this version. In radian, it's this version. Okay, so let's have a look at an example. A circle with centre O and radius 20 has a chord AB. It is 10 centimetres from the centre. Calculate the area of the segment. All right, there's my chord AB. There's the area of the sector that we're looking at. And it says this bit here says has a chord AB that is 10 centimetres. So what that means is that this chord, the distance here that I've put already along there, divided into 2, that distance there is 10 centimetres. and we know this length here is the radius is 20. So what we need is we need this angle at the center here. And so you'll see that I've done a little alpha in there. So if I take that triangle out, so this triangle out there, that's our center, that's A, that's 20, that's 10, and this is the alpha. All right, and so we need to figure out, so we know that cos alpha is 10 over 20, which is half, and so alpha would be cos minus 1 over half, and so that would be pi on 3 for the angle. All right, so the angle theta at the middle, so this angle here, theta, then of course it's going to be twice that. So 2 pi on 3. All right, so now we've got the angle that we require, and we need to pick the area of the segment formula. Now I've given the angle here in radian, because in terms of pi, so it's radian, so I need to use this version here. All right, let's get down here. So the area of the segment is a half r squared theta minus a half r squared sine theta. Okay, half the radius is 20 times 20 squared times theta, which is 2 pi on 3, minus a half times 20 squared times sine of theta, which is 2 pi on 3. All right, so let's have a look at what we've got over here. Numerator, we've got half there that can cancel with that 2. That's handy. Then I've got 20 squared, so I've got 400 pi on 3 there, minus a half times 400 times sine of 2 pi on 3, so that's second quadrant. Second quadrant sine is positive, and it's root 3 on 2 is the value. All right, what do we got? It can cancel here. All right, well, actually, if I go to the next one down, 400 pi on 3 minus 400 root 3 over 2 2's are 4, and then 4 goes into itself once and into 400 100 times. So we end up with 400 pi on 3 minus 100 root 3, and it's centimeters squared. There could be other versions of that if you wanted to have other versions, create a common denominator and do some other funky stuff if you want. But for mine, that's just as good as anything. But be aware if you are looking in your back of the book to check your answers and you get something that looks like that for the answer, it doesn't mean that you're necessarily made an error. It just means that your version is not the same as the way they had. So if I created a common denominator here of 3 and then you take 100 out as a common factor, that's what you end up with. All right, so that's it for those circle things. Circle mensuration, circle measurements, different measurements of circles. Hopefully that's reasonably straightforward. Just remember to choose the version of the formula, whether it's degree or radian, and then you should be right. If you need any help, make sure you get some assistance, and as always, have fun.